Okay, I hope you can hear me. Can I ask first, has anyone heard of POP before? Oh, more than half, great. That's good because we've had a number of workshops with you, so you've remembered. But for the people who have never heard about POP, it'll be a short introduction to our Centre of Excellence and some of the work that we've been doing on new architectures. You'll notice that KNL appears here in the title, and I'll explain that in the course of the presentation. So POP is one of the Centres of Excellence, along with ECHO, that organises this workshop here, that it was set up by the European Union as part of the Horizon 2020 Centre of Excellence programme, and our focus is on performance optimisation and productivity. So we're not focused on any particular application area or application field, but we are transversal, supporting the broadest range of applications that appear. And we offer our services to academics and industrial codes where the developers are located within the European Union, the European Economic Area. The services are available for free, and they come in different shapes and forms. We initially do a performance audit of the code to identify inefficiencies in parallel execution, and then we base follow-up activities on that, where we try and identify and quantify the root causes of those issues and suggest potential remedies and what the benefits might be from carrying out those code changes. And in some cases, we are able to do the modifications ourselves, but actually our experience is that the people who develop the codes are much faster at doing the implementation of the changes themselves, and because they're familiar with the code, and if they get the right directions of what needs to be done, they can implement the changes themselves very quickly. We also provide training with our tools, and I'll follow up at the end. We're using tools which are readily available, tools from Barcelona, tools from ourselves in WYLIE, and these are the other partners who are part of the Centre of Excellence, who provide application expertise and help with different audits, different analyses which are done. We're not exclusively focused on our own tools, the open source tools that we develop. If the audit is for a commercial system, if it's a Cray system or an NVIDIA system, and the tools are available there, we'll incorporate those into the analyses as well. I wanted to give you an overview of the sorts of services that we've dealt with in the 2 years that we've been running this service. On the left here, we've got a breakdown of languages, and probably there's no surprise there that Fortran is the biggest amount there. There's also quite a lot of C and C++, often combined with Fortran. And what surprised us, based on our initial thoughts, is that there's a bunch of other stuff that has appeared. Python appears in all sorts of shapes and forms. That's not necessarily the computational kernel. As we saw yesterday, it's generating the computational kernels, or it's doing some pre-processing, setting up the simulations, but it appears in the workflow, and that's why it's showing up here. And other stuff, wild exotic stuff that we never expected to see. We never see it in the HPC community, but given that our broad basis where we support industrial codes, commercial codes, we see all sorts of Java and MATLAB and stuff appearing there as well. Our focus has been on parallel applications. Most applications are based on MPI parallelization. Some of them are based on OpenMP within a single node, especially the smaller scale codes. And for the larger scaling codes, it's a hybrid combination of MPI plus OpenMP together. Some codes are using accelerators, not exclusively, but in combination with MPI or OpenMP. And again, a wild spectrum of exotic things here. C++ threads, threading building blocks, star PU we heard from yesterday, global arrays, etc., Fortran core arrays. So stuff that's appearing in 1 in 100 cases that we're still trying to deal with, how important these are, how much our tools need to be developed to support them. You probably can't read the legend on here, the breakdown by application sectors. We have chemistry codes, engineering, earth science, CFD, energy, machine learning, and health are the various categories there. And the blue bars are all of the codes together, and the SME codes are the ones which are in orange, where We have a few codes in most of the categories. In some of the areas, we don't have any SME codes. That's been one of the challenges that we've been set by the European Commission, is to get more engagement with SMEs and help them, drag them kicking and screaming towards exascale. Focusing more on what we've been doing for ECHO, for example, we've been working with them from our very early days. We've done audits of the GSELA code we heard about this morning. I'll talk a little bit about ParFlow. Some of these other codes I hope you recognize coming from other centers of excellence. So as well as ECHO codes, the ICON's a climate code from EasyWays. HEMLB is from the CompBiomed for simulating blood flows in the brain. GROMACS from molecular dynamics, I'm sure you know of. Quantum Espresso, these are coming from MAX and from BioXL, COA Centers of Excellence, and Siesta, CP2K as well. So I'm not sure if we have dealt with codes from all of the Centers of Excellence, but we have a pretty broad coverage there as well. Those are the big, well-known codes. There are, of course, many that I can't list here, some of which are commercial codes that I can't talk about, some of which I don't even know about because I've not signed an NDA to be able to access them, but they are part of that breakdown which I showed earlier. When I was invited to give this presentation here, I was very excited because I knew that we had a lot of audit requests to deal with new architectures. What constitutes a new architecture is a little bit debatable. So things like BlueJean, of course, is not a new architecture, but it's certainly representative of something that might be going towards exascale in terms of the number of processes, the number of cores, the number of threads that are involved. Likewise, Spark-based systems like K-Computer, we can deal with codes on those systems up to millions of processes. But that's not new architecture. Is an NVIDIA GPU a new architecture? Maybe, maybe not. We had one audit for requesting, we had various codes that have the capability to use GPUs, like GROMACS is one example, but the audit request specifically said they don't care about GPU performance. The only audit that we had, which was looking at GPUs, we haven't had a good relationship with the customer. They haven't provided a code that we can work with. They haven't done measurements themselves. So there hasn't been any progress there. Same situation with the IBM Minsky system. You heard about Wesson, the example yesterday, Power 8 plus Pascal 100s. There's an audit request, but there's no progress with it, so I can't say anything about it. What I can talk about is KNL, Intel Xeon Phi. There we have had a number of requests, some of which are completed, and I can show you some early results of. Other ones are work in progress or just getting started, so I can't really say anything about those. There was also one audit which was based on KNC, the Knight's Corner, but that's a weird exotic thing, so I'll not discuss that either. A lot of the focus that we're seeing, as well as to support SMEs, is also to give some sort of exascale readiness assessment of the applications. I'm not sure exactly what that means. I would like your ideas, but my impression is that that means scalability to exploit many thousands of multi-core, many-core compute nodes. And an example would be the HiQ club of applications which we have in Jülich, which scale to use the 450,000 cores of the IBM BlueJean Q system there. These are documented on our website. There's 30 or more codes in that list already. GSELA is one of the codes. ParFlow is there. There's other codes I don't think we have running on our system, but there's a whole range, whole spectrum of codes that we have experience with running at what we consider fairly extreme scales on our system in Jülich. The code that I'm going to talk about is ParFlow. That's one of the codes that runs on the full 450,000 cores. It's therefore a member of the HiQ club. It's also one of the ECHO codes. So that's one of the success stories of ECHO and POP working together, was taking this code, which initially had a number of scalability issues, and getting it ready for running on the full BlueGeneQ system, but also getting it ready for running on current systems like Marconi as well. It's a code that is modeling parallel, it's modeling watershed flow, so how water precipitation from clouds flows on the surface of the earth, flows into the soil and the subsoil layers as well. So it's a complex combination of overland flow, topographic information, geological information, and coupled land surface processes. It's a code that's Fortran in C, parallelized with MPI. We were asked to audit it on the KNL system. We had a single KNL available to test on in WYLIE using Intel 17 compilers, Intel MPI, although it's a single node, so we're just looking at single core performance. It was an idealist test case that we were given where I/O was explicitly disabled, and the natural tools that were looking at the vectorization effectiveness were the Intel vTune Advisor tools there. By working with the code, we were able to identify what was not being vectorized well, and then by working on those specific loops and parts of the code, some initial annotations, some initial restructuring was able to deliver a 30% improvement. Adding the appropriate SIMD directive, restructuring some of the loop indices, the loop index order. This is very much initial work in progress, but this is the output we got from the initial vectorization report, which is showing that of the 86 seconds of CPU time, 99% of it is in non-vectorized scalar code. Of the less than 1%, which is vectorized, there are 10 vectorized loops, and the report says that there's only a 44% efficiency from that. So this was a bad starting point. As I said, after some initial restructuring and annotations of these key loops which were identified, we were able to get a 30% improvement, and this is again work still in progress. We heard earlier about the GROMACS code from the BioXL Center of Excellence. Again, we were asked to audit its exascale readiness on KNL. We had generously been given access to the Marconi system at Tunica, which you've heard about several times in the previous days. So I don't need to tell you much about the code, but it's C, C++, parallelized with MPI and OpenMP. As I said, they're not interested in the CUDA performance at this point. Using the compilers which are available in the MPI on Tunica's Marconi system. And the test case that they asked us to audit, I consider to be fairly small. It's about 100,000, 150,000 atoms, and there were 1,000 iterative steps that they were asked to perform. And they wanted us to compare the performance of various combinations of processes and threads, and those are taken care of in the audit report. There's part of it which was a Cree dependence on some long-ranged PME component. I'm not sure I can remember what PME stands for, so I'll just leave it at that. But there was one key option that they asked us to consider including or disabling, which determines how some processes are used to do some additional work and potentially improve the load balance. We were using the Scalasca ScoreP toolset, which is part of what we've been developing at WYLIE Supercomputing Center, doing the initial instrumentation of the code and measurements, focusing on this DO-MD, the molecular dynamics routine, as the main focus of analysis for the audit. For those of you who haven't heard about Scalasca, this is just one slide here. It's a tool that we've been developing over the last decade or more. It's available as open source to be downloaded. It's available as part of OpenHPC. It's also available through SPAC and EasyBuild if those are your preferred mechanisms for getting the tools installed, or you can just download the source code from the website, build it and install it yourself as you prefer. Scalasca is now based on the community-developed SCORE-P instrumentation and measurement infrastructure that's used also by other tools. Tools like Vampire you may know about, tools developed in Munich and the Tau tool set. The initial focus of the Scalasca tools is MPI and OpenMP, but we've also, over the last years, incorporated more threading paradigms, support for CUDA and GPUs in various forms as well. But the main usage is on the very large-scale systems like IBM Blue Gene, the K-Computer, Cray systems, and we also, of course, had support for KNC, no longer particularly interesting. Support for KNL was just build and run. It works without anything special needing to be done there, although we have some projects that are underway to help get additional information about how the memory is used, how the vectorization is used as well. I'm not going to go into any of that. It's something that will appear in future releases. So this is an example of a measurement which was done on Marconi. It's using 2 of the 68-core compute nodes. The execution configuration was 16 MPI ranks, each with 4 OpenMP threads. So it's using the hyperthreading to effectively use all of the resources that are available there. This is a particularly bad execution, which is demonstrated by the fact that there's lots of red here, which is time in MPI. There's a light blue here, a cyan type blue, turquoise blue, which is also inefficiencies waiting in OpenMP. And the worst thing is that while the MPI processes, or while the master thread is doing some MPI operation, all of the other cores are idle, and that's the white part that is the background here. So there's lots of white, lots of cyan, lots of red, lots of inefficiencies which are shown. Also, the computation itself is not very efficient. IPC is less than 1 here. That was execution on 2 of the KNL nodes. We also looked at the scalability, and we quantify efficiencies in a number of efficiency metrics. These are similar to the ones that we heard about yesterday from StarPU. We break down global efficiency into parallel efficiency and computation efficiency, and then parallel efficiency gets broken down into communication efficiency, broken down further into serialization, transfer. So these are all key indicators for us, which allow us to identify what are the most inefficient parts, or which parts are scaling well. In this case, even on a single node, the numbers are pretty bad. Global efficiency is close to 50%, and then adding multiple nodes, it's rapidly going to 0. There's still, I believe in this case, there was still some marginal reduction in time to solution, but the efficiencies are negligible, are rapidly going to 0 here. This is also a breakdown of the proportion of time which is in computation, which is reducing, whereas the amount of time which is in MPI point-to-point, MPI collectives, OpenMP synchronization, all of those are increasing with scale, and the proportion of time which is the idle threads when you're outside of parallel regions and where you're particularly doing MPI, that's growing as well. So lots of inefficiency in this, this test case here. This is actually the better configuration here. So this is with the PME disabled. PME, when it is enabled, is substantially worse. So I didn't include those numbers, but they're in the audit report. I think that's as much as I want to say about GROMACS here. We were given this small ion channel test case to audit. Whether that was a good choice or not, I'm not so sure. Certainly not for exascale scalability. It's completely hopeless. But we were able to identify from the different execution configurations which affinities for bindings were most appropriate on the 68 core KNL nodes. Efficiencies are pretty bad. This automatic distribution that PME is supposed to do is particularly unhelpful, at least on this system and these configurations. We could identify one particular routine, which is for trajectory writing, that is a primary candidate for improvement, that showed up as a key bottleneck in the critical path analysis and the associated delay analysis. So that's one of the main focuses, one of the main parts that we need to be focused on to improve performance of this code. As a follow-up, we're still in, we're actually just delivering this report to the customer as we speak here, so we haven't discussed how to follow up on this, but there's certainly larger test cases that might be more relevant to run where there's 13 million atoms involved. That's a better chance of scaling. There's various execution parameters that GROMACS has that could improve load and balance. Those could be investigated. And the fact that WYLIE always a significant performance limiter, that's also a key thing that could be followed up on. So that's an example of the sort of audit report that you get as the initial service, and then as a follow-up there can be more investigation of specific aspects of this. I include a third code here, which is a benchmark code. It's the BT-MZ, the multi-zone version of block triangular CFD solver. This is a code that we've used and we know runs well and scales on many systems. So it was interesting for us to see to what extent scalability issues are inherent with, for example, KNL, or whether we wanted to have a test case where we could actually have a code that we knew would scale to of order 1 million processes and see how it performs. So this is the largest configuration, class F size. It has two options where you can actually fix the number of OpenMP threads per MPI process, or you can let it balance things. So we compared those two. And the nice thing about this benchmark code is it actually verifies that the results that it got are within the required tolerance. So again, we did our measurements with ScoreP Scalasca. This is an example of the analysis report that's produced. I'm not sure if you can read any of that at the back, but we have a bunch of metrics here on the left-hand side where time is broken down into the proportion of time which is in computation versus MPI, point-to-point, collective, etc., and OpenMP overheads. And then there's these efficiency metrics which are added down at the bottom. So 62% parallel efficiency, 99.5% computational efficiency, communication efficiency, and 62% load balance. So in this application, it's load balance that's the key bottleneck that limits your performance, whereas the communication using non-blocking MPI is scaling without any problem. This is on 1,000 KNLs, so with 250,000 threads in total. We'd like to do some larger tests, but the limits on the queues on Chainic are for 1,000 nodes, so that's as far as we could take it. We'll see if we can get some additional runs a bit later. The key thing here is that there's only 36% of the time is actually used in computation in the computational kernel that's timed for the benchmark. There's about 8% of the time in OpenMP synchronization. Roughly 1% is in MPI point-to-point communication, but when you have MPI done outside of the parallel region, that 1% has to be multiplied by 64, thereabouts, and that means that you have 63 idle threads for any thread that's doing MPI, and that's why the majority of the time is idle threads time here, and that's the main inefficiency. Showing 250,000 threads here in a tabular form is all very nice if you like to scroll down and look at what's going in detail on each rank, on each compute node, on each MPI rank. So here you can see the 4 MPI ranks per KNL, but you need also something that gives you a better overview, and that's why we have a statistical box plot distribution where it's much easier to see that the time for these metrics which are selected here for the computational kernel, which is highlighted here, are varying from around 220 seconds up to 600 seconds. So that's pretty much showing you what your load imbalance is, which then gets fed into these numbers which are shown on the left-hand side. Am I going too fast? So this was a scenario where we're using a fixed number of OpenMP threads, 64 threads per MPI process. On most HPC systems, that actually works out as the best configuration. But on Marconi, it was interesting that we could actually exploit the fact that we're only using 64 of the cores here. There's 4 cores that we haven't been using, and we heard from some of the earlier presentations that using all of the cores is a bad idea, but they're here, there in reserve. So what happens if we try and use those a bit more intelligently? So here's an execution where we let the application balance the number of OpenMP threads it used for each part of the computation. It took the number 64 and added a few more threads on some parts of the computation, took a few more away on the others. So each process is now varying between 62 and 67 OpenMP threads, and we see that the load imbalance here is a bit better. The base time, the fastest time is still around 220 seconds as before, but whereas the slower processes were taking over 606 seconds here, in this case it's now down to 538. So we've substantially improved the load balance by just having a little bit more dynamicism, a little bit more cleverness in how many threads are being used, and the metrics for idleness are improved accordingly. These were just 2 base configurations we ran. There's nothing here that has been optimized in terms of determining what's the best number of threads or the best number of MPI processes. We did do experiments with without hyperthreading, so with only 32 or 16 OpenMP threads. They performed less well, so the hyperthreading was definitely a win here, and the ability to do this dynamically was an even better win for us. So that's a relatively simple code, but I think it already demonstrates that load balance issues and identifying inefficiencies is particularly key when you're dealing with large-scale application executions. In this case, we got a 12% performance gain from the balancing of the threads per process, being able to exploit the fact that we were otherwise unusing some of the KNL cores. Doing the measurements with our tools, ScoreP Scalasca, was straightforward, just the normal compile and run. The only trick here was that typically you have some small number of routines which are executed very frequently inside OpenMP parallel do loops, for example. If you instrument those and collect measurements from those, you have a substantial measurement dilation. You can use a runtime filter to eliminate them. In this case, we used the Intel instrumentation filter, so we told the Intel compiler these are for routines that it shouldn't instrument, and then the measurement overheads reduced to essentially 0 here, and allowed us to scale to many thousands of processes and threads. This is an example from the BlueJean system, just to show that things go well beyond that. This is up to 1 million threads on the BlueJean Q system. Here, the efficiencies are a bit lower. The load balance issues definitely get worse. Here, we're seeing the distribution of time going from 22 seconds up to 570 seconds. So certainly going to more threads, more cores, the load balance issues for this fixed size problem get more severe, but the ability to use the tools, the ability to get the measurements, the ability to see where the problems are all straightforward. This slide is showing that we were also able to do some trace analysis. Whether trace analysis is something that you need to do in every case is a bit debatable here. The traces in this case were half a terabyte in size. Writing half a terabyte is trivial. That was 3.5 seconds or so. But the analysis, examining those traces, took a bit longer. That was about 23 minutes. So there's more work to be done going through the traces, looking and matching the sends and receives to work out how much of the time was waiting for the corresponding communication to take place. At the synchronization operations, which was the last rank to arrive, and what was there for waiting time for the other ranks. But the analysis, the critical path here, identifies which parts of the code are the ones that need to be focused on to improve the performance. And if I can read it here, which you probably can't, it's identifying the main computational do loops, which are OpenMP parallelized here. The most severe one is the Z direction solver of the 3 dimensions, but they all have substantial contributions to the critical path. And in this case, all of the critical path was on MPI rank 0, but it can, in principle, have contributions from each of the other ranks on the system as well. So performance audits on KNL we have found to be straightforward so far. The codes that we've been given to audit on KNL have been codes ported from other systems using MPI and OpenMP, so they typically just build and run. Nothing needs to be done. If the application has some tuning parameters, those can have a substantial effect. We were more or less just running things in the default configuration on Marconi, so the default cache usage, the default thread affinities, everything just worked very nicely for us. And highly scalable codes, we see no problems running to thousands of KNL compute nodes, and doing the measurements with our tools, also no problem. You get a detailed breakdown of the inefficiencies in MPI and OpenMP level. I have a statement here saying that KNL systems may not have fully matured yet. I think they're still getting better. We see improvements week by week for sure. On the Marconi system, we've seen fairly frequent outages of the file system, of the network, kernel updates. I think that's fairly natural. We also see that on other systems as well. I raise a red flag here that we have had a number of unexplained run-to-run variations of more than a factor of 2, where we don't know specifically what's going wrong, but we just resubmit the execution, run it again, and then it's twice as fast. So something is going bad in certain execution configurations. That can be interference from other jobs that are running on the system, which are sort of messing up the interconnect. Yesterday I was talking to Pietro, and he suggested that they had some GPFS file system daemons that were running out of control that kind of interfere with things as well. These things aren't exclusive to Marconi, they aren't exclusive to KNL, but when they happen, they certainly have a significant impact, and that's also one of the dangers of just looking at one execution or one measurement. You're never entirely sure how representative it is. The POP Center of Excellence will be running until March 2018, so it's a good time to apply now, because after that time, we'll try and keep the Center of Excellence running, but we won't have any EU funding for that, which means that you'll probably no longer get the service for free. You'll have to pay for it. This is the website where you can get information about the Center of Excellence. You can see example reports from audits that have been published there. You can apply for an audit yourself of your code. And as I said, we'll do our best to process that if we can before the end of March. If you're unlucky and we don't have the resources, then we'll have to see what we can do. Training is an important part of the Center of Excellence, an important part of the work with ECHO as well. We have a tuning workshop which is coming up at TerraTech near Paris in a week or so's time. That's a free event where you get a chance to try out Scorpy Scalasca, the other tools used in POP. It's actually sponsored by Intel, so Intel will be there to demonstrate and show their tools as well. So that's one of our regular series of tuning workshops. You bring your own code. We help you with trying out our tools and doing some initial performance measurement and analysis there. We also have a full-day tutorial at the SC17 conference if anyone's going to be in Denver next month. That's a more limited environment where we have to work in a conference setting. We will be using the Stampede 2 system at TAC, so another KNL-based system for our tutorial there. But since we're only one day and we have a limited time, that will be limited to some provided test cases. There's no chance as part of that tutorial to work on your own code. What's perhaps the most interesting option here is that the fourth of our ECHO POP performance evaluation workshops. That's going to be in Maison de la Simulation in Saclay in December, so roughly 2 months' time. That's a great opportunity for teams of application developers to bring along their code and to get an in-depth coaching and analysis of their code's application performance. This is a free PRACE workshop organized by the French PRACE Advanced Training Center at Maison de la Simulation. It's co-organized with ECHO. This is the URL for signing up for this. I think it's also available from the ECHO website. I don't think registration is open yet, but I guess that someone will open up registration fairly soon, and then you can apply. Well, put it in your calendar, make your reservations, and then when registration is open, then we look forward to seeing you there. Okay, so thank you very much.